Okay, guys, so we're going to talk about 9.1. This talks about the reactants and the products that are in chemical reactions, and we'll see what that means here pretty soon. So just to back up really quick, what we know is that chemical bonds happen when atoms share or steal or give electrons, and it changes the way that they act magnetically, the way they magnetically attach with electromagnetic force. In Unit 8, we talked about chemical bonds and how chemical bonds are formed. In a great study of a chemistry course, we would actually go back to that unit after this unit with what we've learned, because they definitely do go together. I will make an attempt to get back in that direction, and we can start actually building, doing some what is called stoichiometry and building molecules with what we know about chemical bonds. We take the electrons and put them into the chains of atoms that we build. And if we go even further back, when we talked about chemical and physical changes in matter, we learned that a chemical reaction, or a chemical change, is what we called it at the time, is a change where one or more of the compounds is changed into different compounds. Our typical example of this, and one of the most familiar examples of this, is burning wood. If you take a chunk of firewood, if you take that wood and you combine it with oxygen from the air, okay, and you get it, if you get those atoms shaking around enough, which, if you recall, the kinetic theory of matter says that hot matter is matter where the particles are moving a lot. If you take a piece of wood and you add oxygen from the air and you shake those particles around enough, eventually the oxygen will attach to some of those particles. And we'll get a closer look at this as we go, but this is burning. This is what burning wood is. It's when the oxygen from the air attaches itself to the cellulose, the sugar that is the wood, okay, the hydrocarbon or the carbohydrate. So in that reaction, the reactants are the molecules that will change during the reaction. So in this case, the reactants would be the wood, first of all, but even the invisible reactants, the ones that you can't see because they're gases, like oxygen. So when wood burns, it reacts with oxygen. So these are the ingredients to the chemical reaction. So reactants are molecules that will change during a reaction. These O2s will separate. You'll have an O attached to a carbon over here. You'll have an O attached to a carbon over here. Some of these O's will attach to hydrogens from the wood, and so on. We'll see that when we look closer. Products are what you get after a chemical reaction. In the case of burning wood, the main products, the products that we can see lots of, are actually gases. Most of what is released when we burn wood is not a solid at the end. It's not a liquid at the end. It's mostly a gas. One of them is CO2. So when you burn wood, you release a lot of carbon dioxide, or carbon with some oxygens attached. And also when you burn wood, you actually release a lot of water, H2O, in the form of steam, or gaseous H2O. We think that the product of burning is the ash that's left over, but that's a leftover. It's actually not reacted with the oxygen for the most part. For the most part, the ash that's left over after wood is burning is the part that is not, well, it's not wood. It's the potassium and the things like that that are within the cellulose. So ash it's a leftover product, but the main products of burning are carbon dioxide and steam. So another way to frame this, if we still don't get it, is that in a chemical reaction, the reactants are the ingredients, and the products are the food that you end up with. And this is kind of an interesting way of looking at it, because if you really think about it, your kitchen is the chemistry lab of your home. It is the place in your home where you do most of the chemistry that you do in the home. Almost all cooking involves chemistry. It involves taking reactants and putting them together and usually heating them. And those reactants will yield, or they will give up, or they will produce products. So if you ever wondered, where's the most natural place to do chemistry in the house? Well, it's where you have, a stove and lots of reactants like eggs and sugar and flour. So the reactants are the ingredients, the products are the food. Okay. If you ever get confused, that's how you can know. And the arrow points to the thing you end up with. This is also called the yield sign. I will call it the arrow. We need to review really quickly, again, coefficients and subscripts. Okay, this is going to become more important as we go forward, but the coefficients tell me how many of these chunks I have, how many molecules I have. I have 1, 2, 3, 4 water molecules. And the subscript tells me how many hydrogens are in each. I have 1, 2 hydrogens in this one, 1, 2 hydrogens in this one, 1, 2 hydrogens in this, so 2 in each. Okay. Now, what we will eventually need to do is we'll need to say, well, 4H2O means I have 8 hydrogens and 4 oxygens. Okay. We'll need to be able to do an inventory, sort of a list of the atoms that exist in this set of reactants or products. This will make more sense as we go forward. This is wood burning, by the way. This is the molecule wood, C6H12O6. So each molecule of wood is 6 carbons with 12 hydrogens attached and 6 oxygens attached in there somewhere. This is, I'm actually not sure if this is wood. This might actually be sugar, but they're chemically so similar that we use one to stand in for the other. This is glucose. So this is sugar. Sugar and wood are similar enough. We can consider them sort of the same thing for right now. But here's the molecule, right? You've got carbon, a chain of carbons with oxygens and hydrogens attached, sort of in an alternating fashion. This is a bit of a picture of that molecule, picture of that polymer, it would be called. So it combines with 6 O2s from the air, which is just pairs of oxygen. So oxygen likes to hook up with another oxygen when it's in a pure form. And they yield the CO2 and the steam that we talked about before. Okay. Now, obviously, this should probably be sugar burning, right, or sugar oxidizing, but you guys know about wood burning. It's the same thing. For these purposes, it's the same thing. When we go and we model this ourselves, we'll actually use an even simpler molecule. We'll use one called methane that we've seen before. Methane is, it's basically the simplest hydrocarbon that we can model. All right, I asked you guys to view this video. I'm not going to show this video in class, but if you do not watch this video, there are some understandings, some really important understandings that you will miss. Okay, we need to know what are the reactants and the products of burning. We need to know why atoms glow. So why when we burn things we get light. Okay, and why when we burn things we get heat. Okay, this video does a great job of explaining this. I would love to review that with you, but this is someone else's IP. I'm not going to put it on my video, and I'm not going to take the time to show it again. If you don't view this, you will be missing very important understandings. It's a little silly, but it's great at explaining this stuff. Okay, our first task, identify the reactants and the products in the equation below. So really quickly, this is real simple, right? Whenever you're talking about reactants, you're talking about the stuff to the left of the arrow. Okay. And whenever you're talking about products, you're talking about stuff to the right of the arrow. Okay. So my reactants in this case would be C6H12O6, and the other reactant would be 6O2. Okay. So the reactants are wood and oxygen. My products would be 6CO2 and 6H2O. Okay, so we're going to look at some more of these. Here we have photosynthesis. I'd like to point something out here. Okay. In cellular respiration, that is what your lungs do. Your body takes sugar and it adds oxygen to it, and it yields carbon dioxide and water and also energy from that reaction. It takes those materials and it turns them into these materials, right? Well, photosynthesis is the opposite reaction. Okay, it takes energy from the sun and it adds it to these two, the carbon dioxide and the water, and it will yield the products of glucose and oxygen. So this is how sugar is made. Our lungs work in the opposite way as leaves work. Okay, leaves do this thing, our lungs do this thing. They're opposite reactions. But in both cases, we have reactants and we have products. In this equation, the products are CO2 and water. But in this equation, the reactants are CO2 and water. And the reason we know, the way that we can tell the difference is which way does the arrow point? Okay. The stuff on the left is reactants. Sorry, I'm not writing this with my pen. I was just jotting that down with my finger. And then the things on the right are the products. Okay. It's that simple. One of the ways that in the past I've reminded people, if ever they forgot or they had to check their notes, it's easy to just say, well, the arrow points at products. The arrow points at products. It always points at products. As a matter of fact, time itself is represented by this arrow. Okay, this is the arrow of time, the arrow of thermodynamics. Time gives us products. The arrow points at products. Okay, this one, we have the methane that I promised you, and we have it combining with oxygen, and it will yield carbon dioxide and water. Okay, the reactants are the ones on the left, the products are the ones on the right. Okay, now if I flip this arrow around, the arrow points at the products. If I were to flip this around, then it would make this side the products, but that's not the case. The arrow is almost always going to be pointing to the right, at least in the work we do. The arrow points at the products. Okay, that seems simple, but it's easy enough to get confused by for some reason. We already did. Oh, I was like, we already did that one. Okay, the reactants are over here, the products are over here. Now, this brings us to this interesting idea. It's the law of the conservation of mass, and we've seen this before. We talked about this before when we were talking about chemical and physical changes in matter. So when we first began chemistry back in January, the law of the conservation of mass tells us that the stuff present before any reaction is present after the reaction. And I added a little something to this. It's atoms can't disappear. They don't poof out of existence. Now, they might become invisible. When they spread out far enough, then light will pass through them and suddenly they're a gas and you can't see them, right? You spread this H2O apart. Okay, if you heat it up, it'll spread apart. And if it spreads apart far enough, then you have a gas and you can't see a gas. That's fine. But we need to know that the atoms don't actually poof out of existence. They still exist. And so we're going to do a quick count here. I'm trying to find my pen. There's my pen. We're going to do a quick count, an inventory, right, of these atoms. Okay, so I have 1, 2, it's hard to see there on the back, 3, 4 hydrogens, right? I have 1 carbon, so 1 carbon, 4 hydrogens on this side. And then I'm going to use blue because these are already red. I have 1, 2, 3, 4 oxygens. Okay. My quick inventory on this side and my reactants side. Okay. So we're going to count. We're going to start with our oxygens, right? Just because I already have my blue pen selected. I have 1, 2, 3, 4 oxygens. I have 1 carbon. And I have 1, 2, 3, 4 hydrogens. 4 hydrogens. So in order to see if a chemical reaction went the way we expect, or in order to see this rule, this law of the conservation of mass, all we need to do is prove that this equals this, right? I still have 1 carbon over here. I still have 4 hydrogens over here. I still have 4 oxygens over here. That is the law of the conservation of mass. The atoms don't disappear. They just unhook from each other. They unhook. This oxygen doesn't hook to this oxygen anymore. Now it's hooked to, some hydrogens. Right? This oxygen, it goes to hook to these hydrogens, right? We use colors to do this. This hydrogen and this hydrogen, well, they attach to this carbon, or I'm sorry, this oxygen. This hydrogen and this hydrogen, maybe they attach to this oxygen atom, right? And then the carbon, this carbon, oh, that's not a good idea. This carbon right here is going to attach to these 2 oxygens, right? So they don't disappear. These atoms still exist on the other side of chemistry, on the other side of the reaction. And the reason that these detach, I just want to go back and remind you, the reason that these detach and reattach here and here and here is because when they do that, they better satisfy that octet rule. The electron shells are happier here than they were over here. And this is what causes that arrow of time. Okay. We're not going to dig into the higher physics of that, but time happens because carbon would rather hook up to 2 oxygens than it would to 4 hydrogens. That's why time happens. Okay. Every atom here exists over here. That's the rule. All right, down to our questions. Where are the reactants found in the chemical reaction? They're found to the left, usually. Okay, the products are found usually to the right. Whichever direction the arrow points, it points to the products. If I react wood with oxygen, what would be my products? Right here it is. No, that's not it. Here it is. Carbon dioxide and steam. Okay. The reactants in photosynthesis. Okay, in photosynthesis, we're going to have carbon dioxide and steam. Okay. The law of the conservation of mass tells us that the atoms that exist in the reactants also exist in the products of any reaction. Okay. And the atoms in chemical reactions do not go anywhere. They just reattach. They attach to atoms, to the other reactants in a new way. Okay, it's like if you take apart someone's Lego castle and you use every one of those blocks to build a different Lego castle. Now imagine that each of those Lego blocks is an atom. That is chemistry. That's what happens in chemistry. You take apart the thing and you use it to build a new thing. That's the law of the conservation of mass. Okay, so this primes us for the next step in chemical reactions, where we will start to talk about reactants, products, and leftovers, and we'll start to see how these things are allowed to combine. Because sometimes you don't have enough, oxygen atoms to burn all of the wood atoms, or I'm sorry, you don't have enough oxygen molecules to combine with all of the wood molecules. And we'll see how that works in the next lesson.